the growth rate is related to the growth factor. In fact, 1 plus r is the growth factor. So let's see, if you're growing at 1%, right, then what would r be? 0.01, that's 1%, right? And so what would your growth factor be? 1.01, right? And that's bigger than 1, is it not? Right, so if you want to grow something by 1%, you multiply it by 1.01. You keep what you started with, and you keep adding 1%. So, yeah. So suppose that we do, let's suppose that we do have a growth rate of 1%. So here's an example. Suppose E naught is 10 and r equals 1%, which is also written this way, right? Then our exponential function is 10 times 1.01 to the x. Should we tabulate that? Sure. So at times 0, we've got 10. Right? That's the initial value of our function, if you like, at time 0. You know, I said time 0. Is x time? Not necessarily, but very often we're talking about things that change over time, exponential functions that are time dependent. And so we think of x as being time. And so after 1 unit of time, let's say x is time, 1 unit of time, how big is our thing? Well, it's 1% bigger, right? So 1% of 10 is 1/10. So it's going to be 10 times 1.01, which you could also write it as 10 times 1 plus 10 times 1%. Right, so this is what you started with. This is the amount of growth. So that's 10 plus 0.1, which we can write it as 10.1. Okay, I could have just written 10.1 in the first place, but I kind of wanted to expand it out so you could see what the components are, right? So you've got what you started with plus the amount of growth. Right, so that's your E naught plus R times E naught, which if you expand this, that's what you get, right? So after 2 units of time, there's a couple of different ways you can think about this. You can think about it as, well, the value at 1 unit period, after 1 unit of time, has increased by 1%. And in that case, you would say, well, let's write it this way. We got, right, literally just plugging into the function, right? X equals 2. But you can also think of that as applying the growth factor of a 1% growth factor twice, right? So you grew it by, oh, sorry, what am I doing? I wrote the wrong thing. 1.01 is the growth factor, and we're applying it twice. So after 1 application of the growth factor, we've got 10.1, right? And then we multiply by the growth factor again, which is what we started with. After 1 unit of time, we have 1.01 plus 1% of that, right? So, okay. Now what's that going to come out to? That's going to be what we started with plus 1% of that, which is going to be 1.01. And when you combine those, yeah, you get 11 and 11/100ths. Is that true? Did I do that right? It feels wrong somehow. Yeah, so where did I go wrong? So we have what we started with, grow it by 1% and then grow it by 1% again. So here's the 10 that we started with increased by 1%. Right? So that's this product here, right? And then we're going to grow that by 1%. So that's the 10.1 that we had after 1 unit of time, plus that amount grown by 1%. Yeah, so I didn't multiply by. Yeah, so that was correct, okay. Oh, I see what I did wrong. You see it? It's right here, right? So yeah, I've got the 10.1, but what's 1% of 10.1? We just moved the decimal point 2 places. I only moved it 1. That was my mistake, right? So it's going to be 0.101, right? That's 1% of 10.1, slightly larger than 1/10. And when I combine these, I'm going to have that, right? So you see what happened after 2 applications of the growth factor? You know, so if I grow something by 1% and then I grow what I grew by 1%, I've got more than 2%. That's the point I was trying to make with all this. It's more than 2% bigger than what I started with, right? So growing by 1% and then growing by 1% again is different than growing by 2%. Because it's not the simple interest would be just 1% and 1%. Of the original amount, but this is compound interest, right? So the compounding comes from this exponential factor here, right? And so I could continue on in that factor. So I'm not going to expand it all out like that, but you could. I think what you're going to get is a little bit more than 3%. So basically we're going to grow this by 1%, and 1% of this is 0.10201, right? So if I add 0.10201 to that, I'm going to get 1.03, yeah? Sorry, 10.3. 0301, right? So a little bit more than 3%, right? So simple interest would give you 3%. Compound interest gives you a little bit more, and you might say, well, these numbers don't make a big difference. Well, they don't, but they do make a difference, right? And over time, that can be significant. So. Right, so are we ready to talk about compound interest? Sure. But before we do that, let's talk about, suppose I have a table of values. And I know this is an exponential function. It's of the form a times b to the x for some a and some b, right? And I know that at time 0, I've got, say, 7. And at time 2, let's say, I've got 9. I'm just making up these numbers, right? Is that enough information to determine my exponential function? In other words, can I determine both a and b from this information?
Yeah.
How?
Well, you know that the 7 will be the A.
Yeah, right away. You know that. So A here is what I was using as E0 over there, right? It's the scaling factor or the initial value. And so if you compute E of 0 here, you're going to get A times B to the 0, which is A times 1, or just A, right? And so that means that A must be 7, right? You are. So how about the B?
Well, can we put the points into the equation solve for B?
Yeah, just plug in 2 into the function. We know A is 7, so that's no longer an unknown. So I can say A of 2 is equal to 7 times b squared. And what else do we know?
We know E of 2 is 9.
Yeah, we know that this should be 9, right? So now I've got an equation with only one unknown, b. And I can solve for it. You know, it's not as trivial value. I mean, okay, so you get 9 sets. So b squared is 9 sevenths, right? Which I could write as 63/49. Is that true?
Yeah,
Why did I do that?
because you're about to.
I'm about to take the square root and I want a rational number in the denominator. Quite right. So, so b is going to be, and I'm going to take the positive square root. Why? This b we said has got to be a positive number, right? So this is going to be the positive square root of 63 over the positive square root of 49, which is 7. 63, huh? Can we simplify the square root of 63?
We'll keep 30.
Yeah, 3 times the square root of 7, so I suppose, you know, at some point, you end up with the square root of 7 over 7, all times 3, right? But that means, yeah, so what other functions can you determine knowing only 2 values? Linear, right. If you have 2 points, that determines a line, right? So if I wanted to fit a linear function to these 2 data points, I could also do that. The slope would be what? 2 over 2, I guess? So the slope would be 1, and the y-intercept would be 7. So, you know, if I had L of x here is mx plus b, I could easily determine that n is 1 and b is 7, right? So it's the same kind of thing. 2 points determine a straight line. They also determine a unique exponential function like this. Yeah.
If we weren't given 0, 7, but we were given like 3, 5 or something,
Oh, yeah.
is it not,
Well, that's a good follow-up question to that. So, yeah, let's try that. Yeah, so you might be saying, well, yeah, you were able to compute it easily because you had the y-intercept, right? What if you don't have, what if you have 2 other points and one of them is not the y-intercept? Well, yeah, what if you don't have y-intercept? And that was also made it easy to sort of compute the slope-intercept form, right? Because I knew that b was 7. That's a different b. This b is not that b. But yeah, so let's try another one. So I don't know, 3, 5, 7, 9. I'm just sort of picking up a sequence of odd numbers. So now what do I know? I know e of 3 is a times b to the 3rd, and that's equal to 7, or 5, I mean. And I know e of 7 is equal to a times b to the 7, and that's 9. So what have I got here? I've got a system of equations. 2 equations, how many unknowns? 2. 2 equations, 2 unknowns. If we're linear, I would use like elimination or substitution, one of those things, remember those? But it's not linear. No, so what do? Well, sometimes you can solve one equation for one of the parameters and substitute it, so you can still kind of use elimination, huh? You can solve one equation for one variable in terms of the other, and then substitute into the other equation. Then you get an equation with only one unknown, and you can solve that, and then substitute back.
Could you subtract the
Subtract?
5 and the 3 from the 7 and the 9? I mean, because if a times b to the 3rd power is equal to 5, can you subtract 3 from the 7?
Yeah,
So it'd be
no.
a times 4 equals to 4.
Yeah, so that's an order of operation problem. So you can form the difference of the left side. Let's say a times b to the 7th minus a times b cubed That's the difference, I'm subtracting the top from the bottom, right? So-
That's correct, yeah.
Yeah, so I'd have 9 minus 5 on the other side, right? So, if you subtract equals from equals, you get equals, right?
Right, and that works though, correct? So you.
I mean, this is true, and I got a common factor of a times b cubed here, so I could write a times b cubed times b to the 4th minus 1, and that's equal to 4. Does that help? I've still got an equation with two unknowns.
It looks like we were a variable.
Is this true, by the way? This is equal to that?
You got me. I was kind of hoping to see if it was like.
You wanted to subtract 7 minus 3?
Well, yeah, because then I was thinking that if those two statements there are true, then a times b to the 4th should be equivalent to 4.
Yeah, that's an order of